Hello, everyone. Welcome to yet another UTS QSI seminar. Today, we have the great honor to have Dominik with us. Dominik is a PhD student from Berlin, and he is finishing up very soon. Or Dominik, have you already finished?
So I've handed in, and it's now in the process of being reviewed, which takes ages in Berlin.
Yeah. Okay. Yeah. People in Australia very much understand that. So yeah, everyone wish Dominik a lot of luck with his PhD thesis review, and hopefully you will all enjoy the talk about classical and quantum learning.
Cool. Yeah. Thanks very much for inviting me, Maria. It's a pleasure to be in Sydney virtually, at least. Okay, so today I want to talk about a recent paper that we had with Ryan, Jean-Pierre, and Jens, all based in Berlin. And the paper is about classical and quantum learning of probability distribution. Okay, so we have a quantum computer on the one side and a classical computer on the other side. And the question we ask is how they are able to deal with probability distributions in some sense. Now, okay, so I could give you an entire, lecture series about the same question for, how hard it is to sample for quantum versus classical computers from certain probability distribution. But the question I want to ask today is, how hard is it to learn a probability distribution? Okay, so when we talk about learning, then obviously what comes to mind is machine learning, right? And really this is an instance of machine learning. Or I'd rather say even this is sort of the most overarching general framework for all of machine learning. So let me start out by sort of giving this context from machine learning, and then coming to the sort of more abstract framework in which we're going to ask our question and provide some partial answers at least. Okay, so when you think about machine learning, typically, people show you images of cats and dogs. Maybe they show you sort of paintings of, Van Gogh. Maybe they show you, how machines learn to play chess or learn to play Go. And maybe let's take the first few minutes to see how sort of these very concrete tasks, sort of classification tasks, learning how to play games tasks, and all of that sort of fit into a distribution learning framework. And maybe then more specifically, what machine learning task fits this framework most naturally within the context of learning probability distributions. Okay, so in machine learning, the setting is typically, you have a teacher, let's call it the oracle, and we have a learner, the student, okay? And, the two interact in some way, and the task of the learner is to learn something that, the oracle provides them information about. And typically, machine learning is categorized into three categories. There's supervised learning, unsupervised learning, and reinforcement learning. And okay, so there's some gray areas in between, and maybe there's some more, but these are sort of the most prominent categories of machine learning. So yeah, let's just go through these sort of three categories and see how in each of those cases you learn some sort of probability distribution. Okay, so in supervised learning, what's the task? The task is the oracle provides you with labeled examples of, say, images of cats and dogs, okay? So you get sort of a range of labeled examples of images, like many dogs, and all of the dogs have a 1 attached to them, and many cats, and all of the cats have a 0 attached to them. And then the learner sort of is asked to process those images, and in the end, asked to classify an unknown image. So in some sense, we can say that the task here is to learn a distribution on the set of all images of cats and dogs times 0, 1, okay? So we have a label and we have the image, and we want to learn some distribution on this entire set. Okay, so this is supervised learning. Okay, so why is it supervised? It's supervised because we get labels, right? So we get some info, we really get prior information about sort of which types of images are cats and which types of images are dogs. Now there's also unsupervised learning, where you don't get labels with images, say, so I'm just focused on images, of course, this can be anything, but you just get some images. Okay, so say you get Van Gogh images, a lot of Van Gogh images. And then the task is from the set of all images, to identify images which are Van Gogh images. And this could be, for example, one task in this context could be like, given some random seed, output a new Van Gogh image. On this. So the task here is to learn some distribution on the set of all images. Okay, and then like the last category is reinforcement learning. In reinforcement learning, really we have some game, like in a computer sciencey sense, that the oracle and the learner play. Okay, so there are moves, and the learner sort of tries to optimize the moves over some cost function, right? This is why it's called reinforcement learning. So you get a reward when you win. Okay, so here really we have some distribution on moves, like of the chess figures, conditioned on what the environment is. So what the other chess figures are, and like at what positions the other chess figures are. So hopefully I've convinced you now that, you know, sort of all of machine learning, like in a very like broad sense, is about learning distributions. And today I want to focus like on one sort of like very specific or very specific task, which is unsupervised learning, where we just have some set and we want to learn a distribution over that set. Okay, and we want to compare how quantum and classical learners compare at this task of unsupervised learning. Okay, so let's dig a little deeper into like what really the sort of a more formal statement of the problem is. Okay, so in unsupervised learning, or in just distribution learning, we have some generator of a distribution, like a probability distribution D, and that generator is maybe an algorithm and gets access to, like, say, classical randomness, like for a classical generator I'm looking at now. Okay, so the generator can call like a dice, can throw a dice within the algorithm, and then given the outcome of the dice, it outputs a sample from the distribution. So I call this always in this talk, this gen D, I don't know, my mouse is probably not so visible, this gen D of X. So this is a sample from the distribution D, okay, which is generated by the generator gen. Okay, so this could be a Van Gogh image. Okay, and then, you know, we feed this image, the sample from the generator to a learner. Okay, we do this many times. So we have, you know, some distribution D, and we just feed many samples to the learner. Okay, now you could imagine two tasks at least, but sort of two tasks are sort of like very prominently considered. Like one task you can consider is ask for density learning. So ask for the probability of a given sample. So the task of the learner is now to really learn a description of the probability distribution that it obtains samples from the generator. Another task could be to output a new generator. Okay, so like given samples from the generator, now the task of the learner is to output, say, a description of that generator, approximately or so. And this is the task that we're going to look at today. So the task is, given samples from a generator, learn a generator of that distribution. Okay. But before we can answer this question, it's worth like nailing down the question even further. Okay. So far we have, okay, so the question we asked is, are there distributions which are not efficiently classically generator learnable, but efficiently quantum generator learnable? So is there a separation between the two? How do the two compare? Okay, but as I said, you know, it's really worth nailing down this question as much as possible, so that no bad things happen. And you know, one example where we can sort of see what sort of things can happen is the case of Boolean function learning. So this is sort of a very prominent task that people in computer science considered, where the task is not to learn a probability distribution, but to learn a function. Okay, so we have some function from the set of bit strings to just bits. Okay, and now, you know, you can consider very many like settings, and there's like an entire zoo of things you can consider. So, you know, you can look at different learning frameworks. You can look at exact learning, PIC learning, agnostic learning. Now you can consider different sort of queries you get to the function, membership queries, where, you know, you give the function, your oracle an input and you get the function value out. Random examples where you just get a random value of the function. you could also consider quantum examples where you get a superposition of, function and input pairs. And then you can compare with respect to different sort of figures of merit. You can compare with respect to query complexity for membership queries, sample complexity for example queries, computational complexity, like the overall runtime of the algorithm. And depending on sort of which like precise combination of these settings you consider, you can get very different outcomes, right? So that ranges from no speed up to a super polynomial speed up for quantum algorithms for this task of Boolean function learning. Okay, so I mean, the purpose of this slide is not to like explain everything in detail to you, but just to show you that you can get very different results depending on the specific setting. So, for example, if you look at the exact learning setting and then ask for query complexity with respect to membership queries, like how do quantum and classical compare there, then it's been shown by Kotari that there can be at most a polynomial speed up for quantum computers. But on the other hand, in PAC learning with quantum example queries, like one of the earliest results actually in this quantum learning theory is by Pchuti and Jackson. They showed that if you get a uniform superposition of the function elements in a quantum coherent superposition, then you can get a super polynomial speed up in computational complexity. Okay, so what I want you to take away from this slide is really that the setting, like the very details of the setting, matter a lot. And I mean, this makes sense, right? I explained before that distribution learning is sort of an overarching framework for all of machine learning. And I mean, we don't expect the same things to happen for all machine learning tasks. So really like specifying the task and then asking a very specific question, which is still about a broad class of machine learning tasks, is really important. Okay, so let's do that. Let us specify this question about quantum versus classical learning. Cool. Okay, so the first thing we should ask is, what is it exactly that we want to learn? So I said we want to learn distributions, but do we want to learn any distribution? Like, for what sort of distributions do we want our learner to work? Okay, so of course we have a sample space, so you can always think of sort of set of bit strings or so. And then we have distributions over that sample space. And what we will consider are classes of distributions, sort of distribution also called concept classes. So just some subset of the distributions over our sample space. Okay, and what's really important to talk about sort of scaling, to really compare quantum and classical in this, like in general always, right, is that we can efficiently generate instances. And this will prove to be something that's, that works in our case, but is non-trivial. Okay, so it must be possible that sort of given an input size, like, I don't know, in unary notation, just 1n or so, to efficiently generate instances of the distribution concept classes that we're interested in, like generate distributions from a concept class. Okay, so like as we scale up our problem, it must be possible to efficiently generate those instances. Is everyone still with me so far? Okay, if I don't hear no, then I'm happy. As I said, like, let me reiterate. Just please interrupt me at any point if things are unclear. Okay, so we're considering classes of distribution. So we can specify the question, is there a distribution concept class? So can we distinguish between different distribution within that class, which is efficiently classically generated learnable, not efficiently classically generated learnable, but efficiently quantum generated learnable. Okay, so the second question we should ask, of course, is how do we want to learn? Okay, and now we have, you know, a plethora of settings that are available. Okay, so we can look at sort of what types of generators do we want to consider, what types of oracle access do we want to consider, and then what type of learning algorithm do we want to consider. Like, and many combinations are possible, of course. Okay, so we've already said that we want to compare classical and quantum learning algorithm. So sort of the right half, the right column of this setting is clear. But now, you know, as in the case of function learning, we can really consider different settings in which we compare those two types of learning algorithms. Okay, so you could imagine, you know, a quantum generator, so like some quantum algorithm, and that outputs classical samples in the end. like in this, say, Google random sampling experiment. And the output is a classical sample. And then the learning algorithm gets access to a classical sample. Okay, but you could equally imagine that the quantum algorithm gets access to a classical sample, right? We can feed a classical sample into a quantum algorithm. What we can't do, of course, is have a classical generator and then provide a quantum sample, right? Because a classical generator can't provide a coherent superposition. And equally so, we can't feed a quantum sample into a classical learning algorithm. So there are really some combinations that are not allowed, but still there are many combinations that are allowed. What we want to consider, sort of what's fairest, like from our perspective, is really to have sort of everything classical but the learning algorithm, okay? So we want a classical generator, like an efficient classical generator, and then just get sample access to samples from the resulting distribution. Okay, does that make sense? And then we compare how quantum and classical algorithms compare on learning those distributions that are efficiently classically generated. Right, okay, so we can further specify our question. Is there a class of efficiently classically generated discrete distributions, which is not efficiently classically generated learnable, but efficiently quantum generated learnable with respect to the sample oracle? So the classical sample oracle, we get classical samples from our distribution. Right, okay, so the last question we should ask, what does it mean to learn a distribution? Okay, so I've already said, you know, we want to learn a distribution, but what precisely does it mean to learn a distribution? And the most sort of overarching general framework for learning distributions is PAC learning. Okay, so PAC means probably approximately correct learning. Okay, so we say that a distribution class, remember a distribution class is just a set of distributions over some sample space, is PAC learnable, so probably approximately correctly learnable with respect to some distance measure, if there's an algorithm, A, okay, so now this will be quantum or classical algorithm, which for every distribution in that class and every epsilon and delta, given access to some oracle, okay, so we get some oracle access to the distribution, outputs with high probability, so with probability at least 1 minus delta, a new generator, gen d prime, of another distribution d prime, such that d and d prime, so remember d is the original distribution that we wanted to learn, in our distance measure is less than epsilon, okay? So we have a probably approximately correct learning algorithm. Okay, so what's the setting? Again, we have a learning, we have a classical algorithm, our learner, okay, and then that algorithm can query samples from some efficient classical generator. Then the generator, you know, has access to classical randomness and outputs samples depending on, you know, the classical randomness. And you can repeat that process many times. And then the question is the algorithm efficient in outputting a generator, right? So can we efficiently PAC learn? And what we mean by that is, of course, that the time complexity of the algorithm is polynomial in sort of the input size and 1 over epsilon, 1 over delta. Okay, so one more note. Of course, the distance measure is important, and sort of a standard distance measure is the Kullback-Leibler divergence, because it just has really nice properties and it relates to total variation distance really nicely, which is sort of the operational distance measure and probability distribution. But that really won't play so much of a role for the purpose of this talk, just to note. Okay, so finally, we've got our question nailed down. Is there a class of efficiently classically generated discrete distributions, which is not efficiently classically PAC generator learnable, but efficiently quantum PAC generator learnable with respect to the sample oracle? Okay, so we get samples from the distribution and the Kullback-Leibler divergence. Okay, is everyone happy with that question? Do we have questions about the question that we're asking? Okay, so now we've worked very hard to nail down the question, and the answer will be very simple. Yes. Okay, there's a little asterisk under the decisional Diffie-Hellman assumption for the group family of quadratic residues. You don't need to understand now what that is. I will explain this to you later. okay, but I mean, the theorem is something to appreciate, right? So like you have a classically generated distribution, classical access to the samples, and still a quantum algorithm can sort of exploit the structure of that distribution to do something that a classical algorithm cannot do, namely learn a distribution that a classical algorithm cannot learn. Cool. Give you a second to digest this. Right. Okay. So now we've spent sort of the first, hopefully third of the talk or so, to like specify the question and see the context in machine learning. And I hope to spend the like next half or 2/3 of the talk to give you an idea of how we prove this, like a hopefully quite concrete idea of how we prove this theorem. Because really it's there's no magic behind it or so. Actually, it's really just, you know, digging deep into classical crypto literature. And yeah, I mean, this is something I don't usually do, and I don't know about you. So I'm hoping to sort of explain like these concepts on a sort of intuitive level, so that you can still sort of get the idea, and maybe like if you're interested, look into textbooks or so to understand like these things more in more detail. Right. Okay. So let's look at a proof sketch. Okay, so proof sketch that I will do, of course, has to contain two parts, right? So on the one hand, we have to show that the distribution concept class that we consider, like we have to construct one, right, is classically hard to learn. But on the other hand, we have to show that it's quantumly easy to learn. And okay, so we start from the classically hard part, because this is something that people have looked at a lot in classical learning theory already. And it turns out then that, you know, the quantum part will be fairly straightforward once we have the classical part hit down. Good. Okay, so there's a classical result by Michael Kearns and others, which shows that there are classical distributions that are hard to learn classically. I don't know why I said sample from in the title here. Okay, that are hard to learn classically. Okay, and the basis for all of this is the concept of pseudo-randomness. Now in classical cryptography, of course, pseudo-randomness is sort of a like really basic concept that forms the basis of many like also crypto schemes. And the very particular type of pseudo-randomness that is needed for this hardness of learning result is a pseudo-random function. Okay, so what's a pseudo-random function? A pseudo-random function is a collection of keyed functions. So fk is a collection, k is the key, which go from one set D to another set D prime. And those functions should not be distinguishable from uniformly random functions, like with the same domain and codomain, by any polytime algorithm. Okay, so on the one hand, we have some like collection of functions, which is sort of small compared to the space of all functions. And on the other hand, we have all functions from D to D prime. Okay, and now, okay, so what does it mean to be pseudo-random for this collection of functions fk? It means that, okay, if I draw a uniformly random function from the set of keyed functions, okay, so I draw a random k, and now I give my my distinguishing algorithm, my hypothetical distinguishing algorithm, oracle access to this fk. Like the type of oracle access will matter, and I will talk about this in a second, but I give it oracle access, okay? So A can query fk and it gets results, and then it can process the results. And then the task is to distinguish such a function from a uniformly random function, okay? So say if it's a uniformly random function, you output 1, and if it's not a uniformly random function, you output 0. Okay, so for this instance, A failed. Now we repeat this process many times, both for the collection of keyed function and for the collection, and for uniformly random functions. Okay, and then we say that it cannot be distinguished if the probability over, you know, the problem size and the randomly drawn function, for both, like on the left-hand side, we have the collection of keyed functions, okay, that the algorithm with oracle access to those keyed functions outputs 1, minus the probability that the algorithm with oracle access to a uniformly random functions outputs 1 is negligibly small. Okay, so you really can't treat this algorithm A with a collection of keyed functions. Okay, now, okay, this is maybe a more complicated concept than we had before. So is everybody happy so far with the concept of a pseudo-random function? Yeah, no? Cool, okay, so really, okay, again, the task is to distinguish a uniformly random function from D to D prime from like a function from a small set. Okay, so the pseudo-random function is a small set of functions from D to D prime. Okay, good. Okay, and now there are different notions of what it means to be secure. Okay, depending on the type of oracle access that we give A to the function, we say that the pseudo-random function is like different kinds of secure. Okay, so say we have classical algorithms A, and we get random access to the function. Okay, so we get just random function values output. Then we say that the function is weak secure. If we have membership queries, okay, so algorithm A can query the function on a specific input, then we say it's classical secure. Okay, and then of course we can also do the same thing for quantum algorithm, where we have sort of random quantum access and quantum membership queries, just sort of the quantum equivalent of these classical. And then we call this standard secure and quantum secure. But the concept we will need here are pseudo-random functions which are secure with respect to membership queries. So classical secure pseudo-random functions. Okay, everybody happy? So now say we have a classical secure pseudo-random function, then Kearns et al. Have shown that if I have such a function, then a specific distribution class dk, okay, so now we go from a pseudo-random function, which was a set of keyed functions, to a class of distributions. Okay, so we have the same sort of keys, but now we go from functions to distributions. And we define those distributions by the Kearns generator. And how does that work? We just take an input string x. So remember, every generator has a random input string, like a random seed. We take the input string x, and then we just append the function value fk of x for some fk, like a chosen fk from the pseudo-random function. Okay, so this distribution class, that is the statement of the theorem, cannot be efficiently classically generator learned. Okay, so here I put a little picture. The idea is really that I sort of amplify the uniform randomness of the input seed to the to sort of the double size by appending the function output. Okay, and the idea of the proof, of course, is to show something like, if such a learning algorithm existed, then we could use that algorithm to also construct an efficient adversary for the pseudo-random function. But because we assumed that it was a pseudo-random function, that adversary cannot exist, and hence the distribution class cannot be efficiently learnable. Right. Okay. So now we could sort of stop and say, fine, okay, now I know how to learn classical, now I know how to construct distribution classes which are hard to learn classically. Okay, I don't know what to do quantumly. But it's worth digging a little deeper, because as it turns out, there's a sort of chain of relations how you construct these hard to learn distribution classes. Okay, so we've already seen that once we have a pseudo-random function, we can construct these hard to learn distribution classes. But you can sort of trace this back down to the existence of a one-way function. Okay, one-way function, of course, is something we know from quantum, right? So famously, Shaw showed us how to break certain one-way functions, namely factoring and discrete logarithms. And this is precisely the idea of the quantum easiness proof right now, right? To use Shaw's algorithm essentially to break the one-way function and then sort of break this chain of reductions to hard to learn distribution classes. So basically to take Shaw's algorithm and then construct an adversary for a hard to learn distribution class. Right. So let me now walk you through this chain of reductions. And once we have that, it will be very easy to see how we can break it. Okay? Good. Okay, so we've just seen how we can construct a hard-to-learn distribution class, classically hard-to-learn distribution class, from a pseudo-random function. Now, let's look at how we can construct pseudo-random function. And the concept we need for that is that of a pseudo-random generator. So, what's a pseudo-random generator? Pseudo-random generator is an efficiently computable function, g, again, from d to d prime. So remember that pseudo-random function was also function like sets of functions from d to d prime. And we say that this function is called a pseudo-random generator if the output of the function, given a random input seed, like we draw uniformly from the domain an input, if that output cannot be efficiently distinguished from a uniformly random element of the codomain. Okay, so again, we have a distinguishing algorithm A, and the distinguishing algorithm A gets sample access to outputs of the function g of x, and it gets sample access to uniformly random elements of the codomain. And then the question is the probability that the algorithm accepts minus the probability that the algorithm accepts a uniformly random output, is that negligibly small? Okay, and if it's negligibly small, then of course we cannot distinguish the two, and we say that we have a pseudo-random generator. And again, the probability is over randomly drawn inputs on the left-hand side and problem sizes, and over randomly drawn outputs, so elements of the codomain, and problem sizes on the right-hand side. Okay, and this is important. Okay, oh, I should also say, by negligibly small, I always mean smaller than any polynomial. Because it turns out that if, as soon as you have a polynomial, you can leverage this to, like, you can boost this. Good. Right. Questions on pseudo-random generators? Oh, okay. Good. Now, on the one hand, we now have a length doubling pseudo-random generator. Okay, so we set d prime to just be twice d. Okay. And let's define the output of the function as the first half and the second half, okay, of the output, okay? So we have G0, which is sort of like, always think of bit strings, okay? Like later we will also need other sets, but think of bit strings. Take the first n bits to be G0 of x and the second n bits to be G1 of x, okay? So that's a length doubling pseudo-random generator. So we amplify our random seed to double the size. And now our goal is to construct a pseudo-random function, okay? So a collection of function, like from some key space times the domain to the domain. Such that, okay, again, an element of that pseudo-random function looks random to any polynomial time adversary. Good. Okay, so how do we get from the one to the other? And the idea is actually, it's a very clever idea, and uses, okay, I should also say this, uses bit strings as elements of this domain, which is really important for the construction. Okay, and the idea is to construct some sort of tree. And this is the Goldreich, Goldwasser, I forgot the M construction, I also forgot the reference, GGM in short construction. And okay, now this looks very complicated, but let me walk you through it. Now I take a length doubling pseudo-random generator. Remember G, and that G has the first half G0 and the second half G1. Then I get a key, K, in my key set, K. And I have an input string X, which has n many bits, okay? Remember that our set D, our domain D is the set of bit strings. Okay, so I have an n bit string X, 1 to xn. Okay, so now I want to construct a function fk, or a class of functions, depending on the key. All right. Okay, so I take k as the input. And now k, okay, so I take k as the input, and depending on the value of the input string x of the first bit, I either apply G0 or G1 to k, okay? And then I proceed. So walking through the tree, I start from k. If x1 is 0, I apply G0 to k, okay? Call the output B1. Now, if x2 is 1, then I apply G1 to B1, okay? Call the output B2. And then I proceed through the tree, and in the end, I have a function fk depending on the bit string x as an input, okay? And of course, so the leftmost branch of the tree always has zeros, and the rightmost branch of the tree always has ones, right? So I always apply G1 or I always apply G0. I walk through the tree. Okay, are you happy with this GGM tree, or do you have questions about it? I'll let you appreciate it for a second because it's not so simple. Right. Okay, so this is a really clever idea, right? Because it gives us a lever to take like a single pseudo-random generator, just G, right? Split it in two parts, and then by comparing, by combining the two parts in a complicated fashion, make this tree sort of irreversible, so that you can't learn the key. Okay, because of course learning the key would allow you to distinguish the function from uniform. Good. Okay, so this is this GGM construction and will be very important later. Right, so now we've seen how to construct pseudo-random functions from pseudo-random generators. Now, let's see how we construct pseudo-random generators. Okay, and for that, we will use the concept of a one-way function, actually like a little bit of a stronger concept than a one-way function. And I will first introduce that, and then I will show you how to build a pseudo-random generator from that. Okay, and the one-way function that we will use is discrete logarithm. Okay, so already looming ahead is sure going to break discrete logarithm. Okay, so we need modular exponentiation, right? So take a prime number p, and G a generator of the group ZP, the multiplicative group ZP. Okay, so it has elements 1, 2, 3, 4 until p minus 1. And then we call modular exponentiation with subscript G and P from the natural numbers to ZP. If we just take G to the X mod P. Okay, this should be fairly clear. Right, and discrete logarithm is the inverse function. Given a Y, which is G to the X mod P, output X. And of course, we know that discrete logarithm is a hard thing for classical computers, or assumed to be a hard thing, and crypto schemes are based on this and everything. Now what we will need is a slightly stronger thing than discrete logarithm not being efficiently computable. Namely, that you can't even distinguish from uniform the following. Okay, again, we have two sides, okay? So on the one side, we have the uniform distribution over like our group ZP, okay? And we draw A and B from that uniform, from that distribution, okay? And then we take G to the A, G to the B, and G to the AB, right? And on the other side, we again have the uniform distribution over ZP. We draw A, B, and C, and we take G to the A, G to the B, and G to the C. Okay, and now the task of the distinguishing algorithm is to distinguish those four from uniform, okay? So of course, G to the A, G to the B, and G to the C, they are uniformly sort of random over the group, okay? Because ZP for a prime is a cyclic group. Okay, but on the other hand, G to the A, G to the B, and G to the AB, they are not uniform, right? They have a very specific relation, right? Because, yeah, good. Okay, and of course, if I could do the discrete logarithm, I could distinguish those from uniform, because I could just do the discrete logarithm on all of those elements and then compare C and A times B. If they are the same, I say, oh, you have cheated me. If they are not the same, well, then I assume both are uniformly random. Good. Right, okay, so this is the decisional Diffie-Hellman assumption, that distinguishing G to the A, G to the B, G to the AB from uniform is a hard thing. Okay, and this again is sort of core to many crypto schemes, like practically used crypto schemes actually. Okay, and this is the assumption that we are going to base now our construction for pseudo-random generators on. Okay, are you happy with the decisional Diffie-Hellman assumption? Right. Okay, because now comes some fine print. Now DDH is not believed to hold for any group ZP, for any prime. So for example, if P minus 1 has small prime factors, then we already know that DDH is false. So we have to be a bit more careful into how we choose the group for which we do the DDH, make the DDH assumption. And it turns out that a good group, or like a good choice of the group, is the group of quadratic residues. Okay, so what are quadratic residues? You take a safe prime. Okay, so a safe prime is a prime of the form P is equal to Q plus 1, where both P and Q are prime. And now the group family of quadratic residues with subgroup P are those elements Y in ZP star such that there exists an X in ZP such that X squared is equal to Y mod P. Okay, so basically Y must have a root within the same, like a square root in the same group, mod P, okay? And it turns out that this group family is isomorphic to ZQ. So the order is Q. Okay, so take an example. Okay, we take P is equal 7. 7 is a safe prime, right? Because 3 is a prime and 7 is equal to 2 times 3 plus 1. Okay, set 7 star is then the group consisting of the multiplicative group consists of 1, 2, 3, 4, 5, 6. Good. So now what are the corresponding quadratic residues? QR7. Now QR7 are 1, 2, and 4. So for example, 2 is equal to 3 squared mod 7, and 3 is in set 7 star. Okay. And like you can go through and you will find that all of those 3 elements have a root in Z7. Good. And what will be really important later on is that there is an efficient bijection between QR7 and Z3. Okay, so between the group family of quadratic residues of order P and the sort of isomorphic simple group ZQ. Okay, and how does that work? That works by observing that the quadratic residue group always has exactly half of the elements above Q and the other half below Q, modulo 1. Okay, so 1 is always taken out. Okay, and that makes the bijection really easy because like going from QR to ZQ, you just either take X if X is less than Q, or you take P minus X if X is larger than Q. And so you can just isomorphically map between the two. And then of course you can also easily turn this around. All right, now some more facts about quadratic residues. Quadratic residues are believed to satisfy the DDH property. And what's really important is that a problem instance can be efficiently generated. Okay, and now there are many sort of non-trivial elements. This is what I said before, like instance generation is not trivial in our case, and that come into this. Okay, so the first is membership in the group of quadratic residues can be checked efficiently. The second is safe primes can be efficiently generated, right? Because you might think, okay, so safe prime 2Q plus 1, maybe this is a really hard thing to find for very large Q. But it turns out that you can efficiently generate this. Like given an input length n or so, that I want my size of the key to be, I can efficiently generate a safe prime of that length. Okay, and of course, almost all elements are generators except for 1. Good. Right, okay, so now we have the pseudo-random generator from that. What do? We just define a function g tilde, okay, and we label it by p, the prime, right, which labels our group, a generator for the group, and g to the a, where a is just some element of ZQ. Good. Okay, and that generator goes from ZQ, right? So the small, like Z3 here, to twice the group family, the group of quadratic residues. Okay, and what do? We don't do like as before. No, what we do is we just say, okay, so the first half is g to the b mod p, where b is the input to the function. And the second half is g to the ab mod p. And now you can already see like this is going at ddh again. Because of course, if I could do discrete logarithm, I could distinguish that such a string from a uniformly random string, because I could do discrete logarithm and then compare AB with A times B. Good. I call the first half G0 and the second half G1 of the input string B. Right? Good. And now I can turn this into a function that maps from the same domain to codomain, like twice codomain, by using the isomorphism between QRP and ZQ. Okay, so I just do my G tilde, and then I apply FP afterwards. Remember, FP was the bijection, the efficient bijection. Good. So now we have a pseudo-random generator from the groups of quadratic residues. Happy? Questions? Right, because now we're going to break it. But before that, let me summarize the construction. Okay, so we start from the DDH assumption for the group family of quadratic residues. Okay, so DDH assumption we make for the modular exponentiation, right? G to the x mod p. Good. Then we define the pseudo-random generator, which goes from ZQ to ZQ times ZQ, with some A in ZQ. And we define it by applying the bijection, Fp, to G to the B mod P and G to the AB mod P, where B is the input to the function. And we call this G0 and G1. And this will be important for the GGM tree later, right? Because now we define the pseudo-random function, which goes from ZQ, right? ZQ is the key, times 0, 1 to the n, it's the domain, to ZQ. Good. And we do this via the GGM construction. Then, given the GGM construction, the pseudo-random function from the GGM construction, we define the Kern's distribution class, which is hard to learn. And we have to modify it a little bit because we now want to break it, okay? So we define the distribution class, D, and okay, now we have many labels. P, the label for the quadratic residue family. G, the generator of the group. G to the A, which is the base of like what we do in defining the pseudo-random generator, and then B, which was the input to the pseudo-random function, the key of the pseudo-random function. Okay, and this distribution class, now we define on 0, 1 to the 2 to the n plus m, where m is some number suitably chosen. Okay, and we define it by, as before, in kerns, we do x, we put x in the first half of the output of the generator. Then we take the output of the pseudo-random function, okay, and we binarize it, just taking the binary representation. And then we also append the description of the problem size at the end. And it turns out that doesn't change the hardness of learning result, but will be really important for breaking it. Because, okay, so looking ahead, Shor's algorithm will of course need the base of the logarithm that you want to compute. So it needs G to the A and it needs P. Good. Okay, so this is the construction of a hard to learn distribution class for efficient classical algorithms. Good. Now we are breaking it. Right, so now we will use Shor's algorithm to break this construction. Right, okay, so remember the GGM tree. The GGM tree took a key as an input. So remember our key, key now comes from the group ZQ. And then we walk through this tree by applying G0, G1, depending on the input of the function. Right. Okay, so for modular exponentiation, this looks like this. We take B, some element of ZQ, as an input. And then if like the first input bit x1 is 0, we apply modular exponentiation with base G to B. Oops. Now if the, okay, now we proceed through the tree. Say if the second bit is 1, then we apply modular exponentiation with base G to the A to the result of the previous. Okay, and such we walk through the tree and construct the output of the function. Right. Okay, so now suppose we are given a sample from our hard to learn distribution class that we just constructed. That sample has like the random seed x in the first part, and then binary representation of the output of the pseudo-random function, and a representation of the problem specification, which we needed in the GGM tree. Okay. Now, given the sample, we can just reverse the tree, right? So we take as an input Bn, which is the binary representation of the function output x1, xn, okay, right? So this is just the second part of this sample, okay? So we take this as an input now to the GGM tree, and now we walk the tree back, okay? And how do we do it? We just apply iteratively our efficient bijection, then discrete logarithm, efficient bijection, discrete logarithm, and so on. And such we walk back through the tree. Okay, so applying then 2bn discrete logarithm gives us bn minus 1. And such we walk back through the tree, and in the end we can learn the key b, okay? And then we can output the key. Okay, now it turns out what's really important for this to work is that the quantum algorithm for the discrete logarithm turns out to be exact. Exact means it succeeds with probability 1. Right? So suppose the quantum algorithm was not exact, so succeeded only with some finite probability less than 1. Then the success probability of actually learning the key in the end, because we have to apply discrete logarithm in many steps, like n steps actually, after the other, would be exponentially small in n. So this would be bad, because that would be a negligibly small probability. But fortunately, Michele Mosca and Salka have shown that the quantum algorithm is exact. And so we can reverse the GGM tree and learn the distribution from a single sample. So our learner just gets a single sample from our distribution, like one element of the distribution class, and then we can exactly learn that distribution from a single sample. Now that's pretty amazing, I find. Okay, but now you might also argue it's pretty artificial. Fair enough, we can discuss that later. Right, so let me reiterate. We've asked the question whether there's a class of efficiently classically generated distributions, which we cannot efficiently classically PLC generator learn, but efficiently quantum PLC generator learn from samples with respect to the KL divergence. Okay, turns out we can from a single sample under this DDH assumption for the group family of quadratic residues. Right, so now let me wrap up by maybe discussing like a few pros and cons of our results. So on the pro side, of course, we could say, fine. Now, we have shown that quantum computers can exploit some structure in distributions that allows them to learn those distributions more efficiently than classical computers, even though they just have the same prerequisites, right? I just get classical samples and the distribution is efficiently classically generated, but still there are distributions for which quantum computers can exploit structure in the distributions which classical computers can't. Right. On the other hand, the result is, of course, not a very practical result, right? I mean, who cares about Kearns-generated distributions? And it's also very artificial, right? And okay, so there are two points at which this is manifested, right? So one is a single sample is always sufficient for learning, which is funny. And the learning algorithm is always exact. Okay, so now you suppose you get like put a little bit bit of noise or so on your distribution, then of course this will fail. But in this sort of toy setting where we just have a class of distribution, we are promised that our samples come from one instance of this class, and the task is to distinguish those, then okay, we can learn. But really we want to show like a quantum advantage for more relevant problems. I don't know, say, I don't know, mixtures of Gaussians is such a thing where, you know, you get samples from like some mixture of Gaussians, right? You have a mixture of Gaussian processes, you get a sample and you want to learn the parameters of the Gaussians. Or you want to output new samples, like now this would be density learning, right? Learning the parameters of the Gaussians. Outputting new samples is again generator learning. But then of course there are also other directions. Like remember in the beginning I said what we need is a classical secure pseudo-random function, which is secure against membership queries. Now maybe you could ask, and we discussed this a little bit in the paper, whether maybe weak PRFs, so where you just get random example queries from the pseudo-random function, is also sufficient for hardness. And it seems plausible, but it's very hard to prove because the proof techniques just fail. Yeah, and in this sort of vein, there are like many directions you could go into, like make these things robots to noise, and like for all of these directions, it seems like you really need like new ideas and new proof techniques, because of course, like what I've shown you just now is a very specific problem and like a very specific like way of tackling a problem, exploiting structure of a problem, which is not something that is expected to be generic. Right, and with that, I want to thank you very much for your attention. I'm looking forward to your questions.
Thank you, Dominik. And yeah, thank you for blowing our mind about discrete logarithms. Do we have any questions? Okay, so maybe I would ask the first question. So you show there is a very strong separation between what you can do with a quantum computer and what you can do with a classical computer. Yes. Could you somehow modify your scheme to use it for classical verification of quantum computing, similarly to Urmila Mahadev's result?
That is a good question. That is a good question. I mean, okay. I guess to the extent that you can also use Shor's algorithm directly to do verification of quantum computation, maybe you can also do that. But I mean, no, in the end, I'm not so sure, right? Because we've looked at quantum computers who learn classical distributions, right? But everything that sort of happens on the generator side is a classical thing, right? So we only look at distributions which are efficiently classically generated. And if I understand your question correctly, it would be more about, you know, I have some quantum computer that gives me samples. Can you sort of verify that those samples are from the correct distribution? And then I wouldn't know how to directly apply our result. But still, I think it's a very interesting question. And we've also thought a little bit about how the two things relate, like how learning and verification relate. And it's a bit like in the setting that we look at, it's a bit subtle because we have these classes of distributions only, right? And as soon as your generator, like as the samples that you get are outside of this class, things become funny. And like you could imagine that, you know, there is a distribution which is outside of the class, which sort of fools the learning algorithm in some sense. Yeah. Okay, does that answer your question to some extent?
Yeah. I mean, as much as you think it would. Okay, do we have more questions? Okay, don't be shy, people.
Yeah, I know it's a very dense topic, but I mean, I also know that I probably lost some of you, but maybe you can just, yeah, ask me again about things that were not clear also. Happy to try and explain better.
Okay, maybe people are just too tired to ask more questions. So in that case, If people have, if there are more questions in the future, hopefully we will have a chance to meet Dominik at a conference when things open up again.
Yes, absolutely. Also happy for you to like ask me via email or so. So yeah. So.
Okay, yeah. So let's thank Dominik again.
Yeah, thank you for inviting me, for having me, and